All right, last lesson of Unit 4, our second day of applications of similar right triangles in the field of indirect measurement. Yesterday we talked about indirect measurement. This is where it's either impossible or undesirable to measure something directly. So we are able to use our similar triangles and the proportions that are associated with those similar triangles to solve for measures that we are unable to gather directly. Yesterday we talked about the mirror and the shadow method. Today we'll have something that looks like a bow tie, so we'll kind of call this maybe the bow tie method. All right, you're standing on one side of a creek and your friend is standing on the other side, directly across from you. Your friend is standing 5 feet from the creek, and you are also standing 5 feet from the creek. You and your friend walk away from each other in opposite directions along parallel paths. Your friend walks 50 feet, so this would be 50 feet west, if we put a little north, south, east, and west here, and you walk a little bit more slowly, I guess, or just is not as energetic, and you only walk 12 feet to the east. Now we want to label any congruent angles in the diagram. Now we practiced this yesterday. This is a bow tie, so we know those two angles are congruent because they're vertical angles. Right angles are congruent. We know that's true. And then finally we've got these two parallel lines cut by a transversal. So we have congruent, alternate, interior angles. So like the picture yesterday, we can conclude that these triangles are similar because of angle similarity theorem. Now the key here is we're going to be using these similar triangles with their associated proportion relation to solve for the width across the creek. And we are going to mark that with an X. This is our unknown measure that we will be solving for. And now we need to write a proportion for the similar triangles. So to me, this almost looks like a mirror one, except rather than the triangle being like this for the mirror method, it's flipped over in the other direction. So the triangles are pointing in opposite directions rather than the same direction. Or you could think of it as this triangle was inside here and somebody decided to rotate it out. So it could also look like the shadow method, but this guy is rotated outside of the triangle. Now, so that means the two triangles that I'm looking at, this triangle here, the big one, and then the smaller one here. So again, I have to match up corresponding sides between those two triangles. And so I would have this length here is my 5 plus my X, and that's going to go with this little length here, which is just 5, and that is equal to, now I find the other corresponding sides with information, and so 50, so I'm going from the purple to the blue triangle, or the bigger to the smaller triangle, is to 12. Oh, and I guess I'm going to take this and move it down here. Okay. And now we need to solve this proportion for x. I think I might do a little bit of simplifying here before I solve for x. Can't do anything with the 5 plus x over 5. I do think I can reduce this a little bit, though, and write that as 25 over 6. That's about as simple as I can get. And now I'm going to use my cross product property of proportion. Take the product of the means equals the product of the extremes. Remembering, when I have 6 times 5 plus x, that means I have 6 5s, or 30, and 6 x's. So the width of the creek is 15.8 feet. And like yesterday, we need to have units. This is an application. We're finding an indirect measure. A measurement is going to have units associated with it. Okay, a second problem. It says you and a friend are on a 10th floor apartment buildings that are directly across from each other. So these are the apartment buildings. And each of us have a balcony. I don't know how that's spelled, but that's how it should be. Have a balcony. The two of us are making a banner to hang between the apartment buildings. The wall of my balcony is 4 feet from the street, and my friend's balcony is 6 feet from the street. So this is where my friend's balcony is located, and this is where my balcony is located. Okay, so we have one other set of measurements here to help us build our triangle. It says that from the corner of my building, so if we put some directions here, north, south, east, and west. From that southwest corner of my building, my balcony is 10 feet in from that corner. And my friends were measuring from the other side of his building. We're measuring from the southeast corner, and he is 100 feet from the southeast corner of his building. And we need to determine what the width of the street is, which will be the width of our banner. And so we put X on that segment length. Now we're going to write our proportions based on our similar triangles. And again, I have this orange triangle, and then I have the red triangle. The length of the street is going to be part of the red triangle. So I'm going to go from this big triangle, which is got this segment, the street plus the 6 feet to the balcony, compares to the 4 feet on the smaller triangle. And the 100 feet from the southeast corner compares to my 10 feet from the southwest corner. Or I guess this is the northeast corner. Sorry about that. All right, and now we can solve. Again, I think we can simplify this proportion before solving. That's probably a smart idea. So I have x plus 6 is to 4 as 10 is to 1. 10 divides into 100 10 times. So now I have x plus 6 equals 40. That means x is 34. So the banner must be 34 feet. Now this is a part for you to complete. You are to decide what you think is this method here, which maybe we'll call the bow tie. I guess we've got something that looks like that. Not a very symmetric bow tie, but a bow tie. Is this bow tie most like our mirror method or our shadow method that we talked about yesterday? All right, so moving on to one more that doesn't look like any of the ones that we've studied so far. Doesn't look like a bow tie, and there's no mirror involved here, and there's no shadow. However, we do have a triangle inside a triangle, and we've got some parallel sides, which we've already talked about creates a proportion. We had a theorem about that. And so we also get proportional triangles along with these side lengths of this triangle being proportional. So we need to calculate the distance across the widest portion of the pond, which would be from D to E. And that's our goal. We have some other measurements. The other measurements are that from this point to this point is 16 feet. All the way to one of the points of interest is 35 feet. And then we have this other measure across the pond. Somebody must have measured that a while ago, or it's long enough we can put a string across it or something. Measured that as 20 feet. And so now we're going to make our proportion based on the similar triangles. So again, I've got this small triangle. So in this way, it's like the shadow method inside this larger triangle. So I need to put the corresponding parts together. So part of the small triangle is the side labeled with the 16. That corresponds to the side that's labeled 35 in the larger triangle. And now we'll set up one more ratio of corresponding parts. This 20 in the smaller triangle corresponds to this length of DE that we're looking for. And again, I'm just going to put X because that's, I don't know, less writing to put one letter than two. Looking at this guy, and I'm not seeing anything to help me reduce this ratio at all. We've got an even and an odd. This has only two prime factors. This has no prime factors other than 2. So I'm just going to move on to products of the extreme equals the product of the means. And I get that the length across the widest part of the pond is 43.75 feet. So 43 3/4 of a foot. We have a diagram that looks very similar to this one. Now this one looks more like the shadow problem to me, except unlike the shadow, we have not the collinear points and the measures of, the segments that these collinear points are on that are on the ground, but we've got measures for these collinear points that are on, are what we call kind of the diagonal or the slant. So that's the difference between this and the shadow problems, that we have the information in a different location. But the drawing is very similar. So again, we just have to understand what is proportional here. So I look for the small triangle embedded in a larger triangle. And then I get the corresponding measures. So I have the 280, and that's going to go to, we're not just going to write the 70, because that's not going to be correct. It's going to be the 280 plus the 70. So these were like the problems where we were given our distance to the tree and then the length of our shadow, and we had to add those two numbers to get the length of the shadow. Again, we've got to do the same thing here to get the length of this entire side of the larger triangle. And then that ratio is equal to 20 over what we're interested in, the length across the retention pond. This one I could do some reducing, so I'm going to. Right away I see that I can reduce this by a factor of 10 and end up with 28 over 35. I'm thinking I could do some more reducing though, just to make the math easier for myself. I have a factor of 7 in 28 and a factor of 7 in 35. So now I've reduced this proportion down to something that I could do even without a calculator. I'm still going to use the product of the means equals the product of the extremes. That means the widest part of the retention pond is 25 meters. Again, we have to have the units because we're using this similar triangles for indirect measurement. Right at this point, you are to go back to your warm-up worksheet and go ahead and calculate that length, or excuse me, the width of the crevasse that separates the two people.